Now we're back to the original data set, and our initial objective was to create a prediction model that will help us predict wedding cost using all of these factors. Another thing that it's going to do is help us to find the impact that each of these factors have individually on wedding cost, and particularly the changes in wedding cost. So we can go to data analysis, and we want to make sure you have the data analysis tool pack to access this feature. And I click on it, there is regression here. The Y range is going to be the wedding costs, because this is what we're trying to predict. And our independent variables, or the predictors, are all of these values here. Now the residuals tell you a little bit about the difference between each individual point in relation to the regression model. And this tells you about the distribution of the data. We're going to leave these unchecked for now, and I'll put this in a new workbook or worksheet. Okay, here is the regression model. We already analyzed what R-squared means, but when you have multiple X values, you want to look at the adjusted R-squared, because the adjusted R-squared adjusts for the amount of X variables that you have. So they are a little bit different, but you can say that for the adjusted R-squared, about 70% of the changes we see in Y, which is the wedding costs, is explained by all of these variables. Here is an explanation of some of the more difficult parts of the regression. We can start with the degrees of freedom. This is the amount of observations, or the sample size, minus 1. So it means that in a sample of 25, let's say for the bride's age only, we took the average. So equals average for the bride's age. That is 25.88. So in this sample of 25, 24 of these points can vary. They have freedom to vary, so I can change them. But in order to keep this average of 25.88, this last point would have to be calculated such that the average stays the same. So it doesn't have freedom to vary. So that's degrees of freedom, and it helps us calculate the F statistic along with these two metrics also. They're intermediate calculations for the F-test. So what is the F-test? So the F-test is based on a hypothesis, as we learned in class. So the null hypothesis for this test is that we'll say beta 1 plus beta 2 plus beta 3 all the way up to beta k equals 0. I'll get into what that means in a second. And the alternative hypothesis is that at least one beta value is not equal to 0. So when we talk about beta values, we're talking about the slope of the line that shows the relationship between one variable and the y variable. So if we're talking about the wedding cost and attendance relationship, the beta value is the slope of this line. So it is 130.12. Now, if the slope of a line, if you remember, equals to 0, then that means that as x increases, y stays the same. Or as attendance increases, wedding costs stay the same. That means that x has absolutely no effect on y. So our null hypothesis is that none of the variables in the model has an effect on y, or can explain changes in y. All right. And the alternative hypothesis is that at least one of these variables can explain changes in y. Now, you may have seen this normal distribution plot before when we think about hypothesis testing and t-tests. And it's based on the idea that if we take this sample and run it 1,000 times again, or even more, and we document the F statistic of each of those samples, it'll probably form a distribution that looks something like this. And our null hypothesis for this distribution, or for what the F-test will be, is that it will equal to 0, which means that the mean of the distribution will equal to 0. And now we have to see if this F statistic that we have for this specific sample can allow us to reject that null hypothesis. So the F statistic is calculated in this way, and I don't want to get too much into the numbers of it. It'll look like this instead. Variance of group means over mean of the within group variances. And another way to look at it is the explained variance over the unexplained variance. Looking at this equation logically, we can see that if the explained variance equals to 0, that means that the variance of group means also equals to 0. So each individual group is really identical to each other. So no individual factor can on its own explain for changes in y. And so if the F statistic is equal to 0, F stat equals to 0, then of course we do not reject our null hypothesis, and that means there is no explained variance. In our particular case, the F stat is pretty high. It's 12.22. So right off the bat, we can say there is enough evidence to reject the null hypothesis and state that at least one of these variables have an effect on y. And not to get too much into the details of it, but we would actually compare the F stat to an F critical value. Similar to how we would compare a T stat to 2 and -2. And 2 and -2 would be the critical values. We'll get into that later. But the F critical value here is shown in the textbook on page 640. So it's a chart. But this is actually what the distribution of the F critical values look like. So this is saying that this is what the distribution would look like if the null hypothesis were true. So it falls between 0 and 6. If your F statistic is greater than 6, you know for sure you have enough evidence to go ahead and reject your null hypothesis. But if you're not really sure and your F statistic is between 0 and 6, you can do one of two things. You can go to your textbook and find the F critical values at the correct degrees of freedom, which in this case would be 5 and 19, and you can compare the F to the F critical. If the F value is greater than the F critical, then you can reject your null hypothesis. The second thing you can do is look at the significance F. If your significance F is less than 0.05, you can reject the null hypothesis. Why does this work? Because for this hypothesis test, you want to have 95% confidence in rejecting the null hypothesis. That's usually the standard level of confidence, which means that you're allowed to have about 5% error. The significance F is similar to the p-value because it's measuring the amount of error. So if your error is less than 0.05, you can reject your null hypothesis because you have 95% or more confidence. So in class, we heard that the rule of thumb is if the F is greater than the F significance, or significance F, we can reject the null hypothesis. So in the situation, for example, where F is really low, so close to that null hypothesis of 0 here, and the significance F is really high, which means that there's a lot of error or uncertainty in rejecting the null, in that case, we wouldn't reject the null hypothesis, and we would conclude that none of the variables in the model have an effect on y. This rule of thumb is kind of like estimating or eyeballing the results of the null hypothesis, as opposed to directly comparing the F to the F critical value. But if there is a case where your F stat is between 0 and 6, then you will get a better estimate on your hypothesis by either comparing the F stat to the correct F critical or comparing the significance F to 0.05. All right, now we're in the final steps of analyzing this regression model, and we want to be able to look at each one of these X values and figure out if they individually have an effect on our Y value, which is wetting cost. And we're going to do that by looking at the T-stat and the p-value. So similar to our F-test, the T-stat is based on a hypothesis. The null hypothesis is that the slope of any individual x value that we see here is equal to 0. So this x value has no effect on y. And the alternative hypothesis is, you guessed it, the slope is not equal to 0, which means that any one of these variables does have an effect on y. And again, we have our normal distribution, which is based on the idea of if we ran a whole bunch of samples again that were identical to this one and documented the Tstat value, our null hypothesis would be that the average or the mean of this distribution is 0. And we want to figure out with each of these t statistics if it falls in the rejection region or if it falls in the fail to reject region. And our critical values for this is -2 and 2. That's based on a 95% confidence. So if a t statistic is above 2 or less than -2, we can say that there's enough evidence to reject the null hypothesis in favor of the alternative, meaning that this distribution's mean for any of these x values is not equal to 0. So let's look at bride's age, for example. So bride's age, the t statistic is -1.13. So that falls right around here, 1.13. So it's still in the rejection region. So we would say that the bride's age has no effect on y. So we would fail to reject the null hypothesis. However, if we look at couple's income, it's all the way over here, 4.10. So we would say that couple's income does have an effect. Okay? And because of that, when we look at all of these t statistics, none of these have an effect on wedding costs because they're all within this rejection region. The only one that does have an effect is couple's income. So if we were to run a regression model again using only the useful x variables, we would just have intercept and couple's income, because each of these other variables are proven to be not useful in this prediction model. And just a quick look at the p-values, it's very similar to the significance f that we saw in the Ftest. For couple's income, the p-value is less than 0.05, which means that there is less than 5% error in rejecting the null hypothesis. So there's 95% or more confidence in rejecting that null hypothesis. Whereas these large p-values tell us that there's a lot of error involved in rejecting the null hypothesis, so we go ahead and keep the null hypothesis because of these high p-values. Back to Excel, I ran a regression just using couple's income to predict wedding costs because we found that this was the only useful variable. So now let's do some predictions. So couple's income, and let's say we want to predict the wedding costs for a couple whose income is $100,000, another couple whose income is about $54,000, and then let's go with maybe $35,000. And the way we're going to do our predictions is equals to the slope or the coefficient for couple's income times the couple's income that we're trying to predict plus the intercept. And because I'm going to drag this down for each one of the couple's incomes, I'm going to lock in this one and the intercept. And now I can drag it down and change it to a $sign an accounting variable. So now we can say that wedding cost prediction for a couple whose income is about $100,000, their wedding cost may be around $36,000. But for a couple whose income is about $35,000, their wedding cost might be around $9,500. So these numbers actually make a lot of sense when we think about it logically. But based on our prediction model, this was the one variable that was most useful in predicting wedding cost. Okay, I hope this was helpful. You've got to look at multiple regression and finding out which variables are useful in a multiple regression model.